So this is where that little bit of calculus that you might be a little behind on comes in. But it's one idea, and it's not a very complex idea. You have three things: position, what else?
Velocity?
Velocity, and what's the last one?
Oh man. Acceleration.
Yep. Position, velocity, acceleration. And these are typically in terms of time. So, well, you'll have position in meters or something, velocity in meters per second or something, acceleration in meters per second squared, something like that.
Okay.
It'll always be a distance, and then a distance over a time, and then a distance over a time squared. So if you want to go from position to velocity, and say you have some equation for position, what do you do to try to get velocity from position?
Divided by time?
Sorta. You take the derivative with respect to time.
Okay.
So these things are a derivative. And then, have you kind of talked about, do you know what a derivative is as opposed to an integral? Like,
No idea.
okay, so when you take the derivative of something, you're moving kind of down, you kind of go down layers. And we'll talk about what it means graphically in a second. But the integral kind of reverses the derivative.
Okay.
Okay, so this is the integral. This is the derivative. Okay. We won't get into the math so much of it, but we'll look at what it means graphically because that's the important part for the graphs. So if you have position and you want to get velocity, then you want to do a derivative. If you have velocity and you want to get position, you want to do an integral. So let's talk about the graph now. Let's say this is my position graph. And this is position, so say x in meters over time, so time in seconds.
Okay.
If we wanted to find velocity from this, what does it say we do? Take a derivative, right?
Okay, what's a derivative? Did you just say that? I'm sorry.
No, so I'm trying to keep from explaining it like too far in depth, the total calculus idea. All I was looking for is just to get from here to here, you just follow this arrow. So it says you do a derivative, whatever that means for right now.
Okay.
So a derivative means you're finding the change, like how quickly it's changing versus in terms of time.
Okay.
So you say the derivative of s, so s prime equals ds dt. All this means is it's a really tiny change in position over a really tiny change in time.
What is S prime?
So that's just kind of how you annotate the first derivative of s.
I think this is what we're going to learn
In calculus, yeah, you'll definitely go over all these things, but all this means is say, okay, let's take a tiny little change in position, so this, and how much time did it take to make that change? Well, this distance right here.
Okay.
Tiny little change in position divided by a tiny little change in time. Actually, it's easier to look at if you do it this way. So a tiny change in position over a tiny change in time.
So it's your slope.
Yep. So graphically, your derivative is represented by the slope of a graph. And just like we see here, so ds dt, this would be in meters per second.
Okay.
So now you can see why, oh look, if we have position and we go to meters, if we do ds dt, it gives us something in terms of meters per second.
What does ds over dt stand for?
So this is kind of what we use when we're taking derivatives, because to take an actual derivative, so for example, you have a curve that looks like this, we can't, at this point now, we can't say, well, let's find what's the change here and change here. Because that would give us a slope that looks like this.
Uh-huh.
And say we're trying to find the slope right there, you know. The slope's actually like that.
Tangent.
So you have to find a tangent. So what you actually end up having to do is take this distance and then you just make it smaller and smaller and smaller and smaller and smaller until you're working with a change in position that's zero, basically,
Right.
over a change in time that's basically zero. But it gives you a tangent slope, and that gives you the value of your derivative
At that point.
at that point. And then it changes, right? So over here it'll be like this.
Mm-hmm.
But for simplicity's sake right now, because that's, you know, so that's why they use ds and dt. That means tiny little change in s and a tiny little change in time.
Okay.
But they would still be in units of meters per second. So now we can see, okay, the derivative of position,
The D stands for delta then.
yeah,
Okay.
yeah, basically. And then, so the derivative of position would be, oh look, this is velocity. So then if you have acceleration, you want to find acceleration. Acceleration equals dv dt. This means the first derivative of velocity. So you take a tiny little change in velocity over a tiny change in time. You can see, oh look, that would be the slope again. So the slope of the velocity graph will give you acceleration. Well, dv over dt, so this would be meters per second over, second. This is meters per second, or meters per second squared.
Okay.
All right. So we don't want to get, sorry, I'm getting a little off track
No,
there.
it's good. I'm starting to like see it. Like when you draw the picture, if you threw numbers on there, I can tell you what the slope is. But
Yeah.
it's this stuff that I'm having trouble with. So this is good.
Yeah, okay. So with that, just that information so far, let's, without numbers, because they do this a lot to us, let's just kind of bring this graph down. We'll make another graph. We'll call it velocity in meters per second versus time in seconds. Okay, and then we'll just kind of draw some lines to line up with the changes here. And then over here. So this first section, what is your velocity? Would it be positive or negative?
Positive.
Positive. And would it be, like, how big is it going to be?
I don't know.
It'd be, well, you just kind of have to estimate, right? You just say, well, that slope, it's fairly steep. Let's just say it's up here. And then what kind of line would it be?
A straight line.
Just a straight line right across.
It's a steady.
You have a steady slope, exactly. What about here? What's your velocity graph going to look like?
That's a standstill.
Mm-hmm.
So it's straight down. Wouldn't it be?
Yeah, so it goes straight down here and then it stops. So the velocity graph isn't smooth. You can see where these sharp turns are.
Right.
That means it changed velocity in an instant.
Okay.
So from this section though,
From just right on the x-axis.
yep, because that whole time, this entire time, it's not moving.
Uh-huh.
And what about here?
It's negative.
Yep, and is this one steeper than this one?
Yeah. Steep.
Yeah, so it's probably more negative, maybe down here somewhere.
Okay.
And just like you said, if you had the numbers there in front of you, it'd be a piece of cake to find out exactly what it is.
And it goes back to 0.
0.
And even more negative.
Yeah,
Even steeper.
so it'd be down here somewhere. Okay. Now, let's look at the other direction for a second. And the same thing applies if this was if this was velocity and you're trying to get acceleration.
Okay.
Works exactly the same way. There's no change. You just find the slope of the velocity graph will give you your acceleration. Now let's say,
The slope of the velocity graph?
yeah, so if you want to keep going with this one, what would be your acceleration for this whole thing?
Oh, do you find an average? I don't know.
Well, here, let's do it just like we did. We'll just draw down here a little bit more. Some of them need to be very big. You'll see why. So this is acceleration in meters per second squared. So now we're looking just to our velocity graph.